Next up we have Kira Shaw, who is a postdoc in Catherine Hall's lab, and researches neurovascular coupling in the mouse brain, not the human brain, in particular the hippocampus and visual cortex. And you've written a novel.
Yes.
That she hopes to get published someday.
Yeah, one day.
What's the genre?
I don't really know.
Thriller, romance, science?
It follows a boy who's born with Down syndrome growing up this, so I don't know what the genre is, but it's not exactly overly cheery.
Very talented. Oh, and the title of Kira's talk is Energy Supply in the Brain, What Happens When It Goes Wrong.
Thank you. So, as Chrissy mentioned, I'm having a bit of a memory glitch today, so I'm going to have my notes at the side just in case. So good afternoon, my name is Kira, and today I want to talk to you about energy supply in two different regions of the brain. But before I get onto the brain, I'd like to start with a little scenario. It begins with your best friend and her beloved fluffy pen. Now, over the years, you've always eyed that pen with some jealousy, but you have your boundaries and you know that it is hers. Now, one day, this fluffy pen goes missing and she accuses you of stealing it. No matter how much you object, she just doesn't believe that you didn't take it. But she does have a solution, and that solution is for you to take a brain scan to prove your innocence. Now, you would feel sure that it would come up that you weren't guilty, wouldn't you? But only if that brain scan was accurate. Now, there's actually a company in the USA called No Lie MRI, and they hope to eventually use this technology in courts of law. So this isn't for the minor petty theft of a fluffy pen, but for more serious crimes such as rape or murder. The problem with this is that fMRI is far from error-proof. In fact, a team of scientists put a dead Atlantic salmon into an fMRI scanner and they found brain activation. There's something fishy about that. So in the case of the salmon, they found brain activation because the proper statistical corrections were not made afterwards. But there are a number of reasons why fMRI scans may not always be entirely accurate. So in my research, I researched the brain activity that underlies these brain scans in the hope to better understand them. But before I go into that, I want to tell you a little bit more first about how fMRI works. So fMRI does not directly scan your brain cells. Instead, it measures the blood in your brain. And the blood is there to supply these cells with oxygen, which means that if we see more oxygen and more blood to an area, we assume that the cells are working harder. So it's a little bit like trying to guess the number of people who attended a festival based on the empty beer cans they left behind on the grass. So for my research, I'm able to see both the blood changes and the brain cell changes. So I can see both the festival goers and the empty beer cups. So it's the hope that this kind of research might help other scientists to better interpret their data. So if you take a small chunk of brain tissue and you zoom in until you see an individual brain cell, you'll notice that nearby there's likely to be a blood vessel. And as we now know, the blood vessel is there to supply the brain cell with oxygen to give it energy when it becomes active. And it does this by dilating, and that allows more blood into the area. So this relationship is aptly named neurovascular coupling. So I study neurovascular coupling in two different areas of the brain, the visual cortex and the hippocampus. So now I have a prop. So the visual cortex is part of the neocortex, and that means that it's at the surface of the brain. It's specifically here towards the back. And as you can tell from the name, the visual cortex is important for visual processing. The hippocampus sits somewhere below the neocortex around here, and this is important for memory and navigation. So I have measured the brain activity and corresponding vessel diameter changes in the visual cortex and hippocampus of mice. So, is there a laser? Oh, I'm going to use my hands. Okay, so the green trace, can you see it? The green trace represents the brain cell activity, and the red trace represents the vessel diameter. So if I start in visual cortex, you can see that as the green trace increases, so the brain cell activity increases, you get an increase in the vessel diameter. So if we take that back to our fMRI scan would be accurate because it would be reflective of underlying neural activity. However, in the hippocampus, this isn't always such a straightforward relationship. So in this case, you can see that there are increases in brain cell activity which match the magnitude of those seen in the visual cortex, but that there are no corresponding changes in the blood vessel diameter. So if we now take that knowledge back to our fMRI scan, it would look like the hippocampus wasn't active, but actually it is. So just because the field has no empty beer cups in it doesn't mean that no one attended the festival. I also took further measures to try and understand this a little bit more of brain cell activity and blood flow. So oxygen consumption is a correlate of brain cell activity, so that's the bar chart in green. And we found that there was no significant difference in resting brain cell activity between the hippocampus and the visual cortex. But what was different was that the visual cortex had significantly higher levels of blood flow and oxygen to the region. So this means even though the energy demand was the same across the two regions, the energy supply was lower in the hippocampus. And not only can this kind of research shed light on fMRI studies, but it can also be relevant to research into neurodegenerative diseases such as Alzheimer's disease, which could be triggered by a failure in the brain's energy supply. So neurovascular coupling is a critical mechanism for maintaining brain health. But in Alzheimer's disease patients, for instance, they've actually seen that there is reduced blood flow and oxygen in the brain before the onset of clinical symptoms such as memory loss. And because of their high demand for energy, the brain cells are particularly sensitive to a lack of oxygen. And a lack of oxygen in the brain is a condition referred to as hypoxia. And as we have already seen, the hippocampus is particularly vulnerable to hypoxia. So if there is a long-term restriction in the amount of energy that is supplied to a brain region, then this can cause the cells to stop working correctly, which could lead to cell death and even cognitive deficits. So to summarise, in our lab we have special imaging methods to measure both the blood and the neural activity in the brain. And I hope that I've emphasised and convinced you of the importance of this kind of research to help us understand fMRI, and also the importance of maintaining an energy balance in the brain. And finally, to conclude, I think that my friend Orla is just going to have to take my word for it that I didn't steal her fluffy pen. Thank you.
We have a few minutes, 3 minutes for questions. You're just being lazy now here.
Thank you, and it's such exciting work to be able to understand the neural basis of the work that, for example, Chrissy and I do. So it's maybe a little bit of a tangential question, but I wondered what your thoughts were on how neurochemistry might influence some of these processes. You know, for example, dopamine, noradrenaline, because in a condition like Tourette syndrome, people are often on a lot of medications that increase the transmission of those neurochemicals. So it's possible that this impacts on the bold responses that we see.
It's a little bit out of my comfort zone, but I guess if these were causing changes to the neural activity, then as far as neurovascular coupling goes, you could definitely see changes to the bold response. But I'm afraid I don't know much about that.
Something for the future.
Yeah, thank you.
I think we have a question in the back.
I think it's really interesting. I was interested in the difference with the hippocampus, and I was curious, well, I don't know a lot about this work, but would the size of the different regions matter in terms of thinking about the relationship between the oxygen and the energy and the bold response? Or how do you account for that?
I think that one of the main factors possibly that, or one of the main theories for why the hippocampus may not have the same sort of regulation of the blood into the neural activity is actually that there's less vessels in that area. So rather than the size of the area, I think maybe it could be linked to the vascular density. So if there's less blood there to supply, less likely to supply the neurons.